In this lecture, we will overview important transport parameters, and based on those transport parameters, we will also define different transport regimes. In the beginning of this lecture series, we mentioned that the quantum transport applies to quantum confined systems. The three-dimensional bulk materials, the everyday materials that we see, the everyday devices that we see, such as resistors, capacitors, those are bulk systems, and we do not observe any quantum transport phenomena because there are no quantum confinement effects there, because the charge carriers, such as electrons, are free to move in all the directions. Now, the two-dimensional systems, what that means is the electrons are confined move in a plane in two dimension. What that means is one of the third dimension doesn't exist, or in that direction the electron is not free to move. One of the most popular example is a sheet of two-dimensional layered system such as graphene, and there are also bulk two-dimensional systems. When I say bulk, what that means is the material as a whole is a three-dimensional system, but the electron is confined to move in a small area, in a small region between the interface of two different materials. For example, the gallium arsenide and aluminum gallium arsenide interface. Those are called quantum well heterostructures, where you have a two-dimensional electron system which is confined at the interface between gallium arsenide and aluminum gallium arsenide. Now, if you reduce one more dimension, then you get the one-dimensional system, carbon nanotubes or nanowires, where the electron is confined to move only in one direction, say for example x direction, but other two directions are so small that electron cannot move in those two directions. Those are the two-dimensional systems. Now, eventually, if you reduce one more dimension, you will get to zero dimension, but we will refer to the zero dimensional as quasi-zero dimensional systems. Quasi-zero dimensional system, because there is nothing called zero dimension. There is some dimension itself, so we call it quasi-zero dimension. Here, the electrons are confined in all the three directions. For example, the C60 molecule or the buckyball is one example. Okay, then quantum dots, those are small conducting regions in submicron scale, a few tens of nanometer scale sometime, which are grown by various material growth techniques. Those are called quantum dots. Those are also nanoparticles. In these systems, the electrons are confined in all the three directions, and we call them a zero-dimensional system. Okay, so the quantum transport phenomena, whatever we are going to discuss, falls into one of these three categories, either two-dimensional, one-dimensional, or zero-dimensional system. And roughly during this course, we will start with the two-dimensional system, and roughly we will march down in dimension and eventually stop with the zero-dimensional system. That is the way the course is planned, but sometimes there will be some overlap or some mixing. All right, now let us start defining or overviewing what are the important parameters. Probably the most important parameter would be the Fermi wavelength, or lambda f. This parameter we already have defined in the previous lecture. So it is the wavelength or de Broglie wavelength of the electron or the charge carrier at the Fermi level. When I say at the Fermi level, what that means, that electron or that charge carrier has a wave vector of kf. Kf is something which we already have defined. Okay. If you consider the one-dimensional system, say particle in a box, this Fermi sphere is for 3 dimension. Okay, it's a one-dimensional system. That is a particle in a box problem. It's a 1D. So when you add electrons to the system, they will go to the successive quantum levels. Okay, and the last field level is called your Fermi level. Say for example, in this case, it is n is equal to 5. The wavelength, the de Broglie wavelength of that particular state or electron belonging to that particular state is the Fermi wavelength lambda f. Okay, and you can see that the Fermi wavelength will keep on reducing as you increase the number of electrons or as you increase the filling. Okay, and the wave vector corresponding to that state is called Fermi wave vector. And you can also define a temperature scale for that particular wave vector or particular state that is called the Fermi temperature. What you do is you just need to take the Fermi energy, that is EF, which is h bar square k f square by 2 m, and equate that to kBT F. So this TF is called your Fermi temperature. Okay. The velocity that you can extract from this kinetic energy term, that is called the Fermi velocity. The velocity that you can extract from that kinetic energy, that is your Fermi velocity. And in quantum transport, or to understand or to classify whether the system is going to execute quantum transport or not, probably the most important parameter is the Fermi wavelength, because you always compare the dimension of the system with the Fermi wavelength of electron. That is how you say whether that system belongs to, or whether there is a confinement effect or not. The comparison to Fermi wavelength. The system is sizes comparable to Fermi wavelength, then you can say that you have the quantum confinement effects in action. That we will define in a minute in detail. Okay. Now, the second parameter, which is also very important, is a mean free path. Mean free path, which we already have discussed in the context of Drude's theory, that is the distance the electron travels, the mean distance the electron travels between successive collision under the action of an electric field. But in general, the electric field that you're talking about in transport is really, really small compared to the Fermi energy. So you can think that the electric field is really negligible. I mean, the potential due to the electric field is negligible. Okay. So you can define a mean collision length or scattering length, Lm, with the Fermi velocity and the mean collision time, Tm. Okay. So what I'm trying to say here is this Lm is not really a function of the applied electric field or the voltage that you have applied across the material. That is a property of the system, and that depends on various parameters such as how many defects are there, what's temperature, a lot of other effects. But it's not really a function of the applied electric field in the normal condition, or what we say is a linear transport regime. Now, the way this is defined is it's the mean distance the electron travels before it resets or before its initial momentum is completely destroyed. Now, unlike the Drude's picture, here you don't need to worry about whether the momentum is completely reset or not. I mean, momentum has gone to zero or not. Here, electron always will have momentum because those are quantum mechanical objects. As long as they have a wavelength, they'll have momentum. Okay, de Broglie wavelength, they will have momentum also. Okay, it's not that the momentum is zero. Momentum is zero belongs to the wave vector zero because momentum is h bar k, but wave vector zero lies in the middle here. Okay, but the particle which lies in the middle cannot move because there are no empty states around. Okay, so we are always discussing about the particle or electron or the charge carriers at the surface or close to the surface of the Fermi sphere. All right, now after the mean free path, we are going to define two more mean free paths. One is the elastic mean free path, LE, that is the distance the electron travels between two elastic collisions. When I say elastic collision, means there are no energy exchange. The electron is going to retain its energy before and after. Before whatever the energy it had before the collision is going to retain that energy, and that is the elastic collision, and that is the distance between two elastic collisions is the elastic mean free path, which is generally defined as LE. And one of the example for the elastic mean free path is the collision between electron and one of the impurity atom. You can think of, like, say, a relay hard sphere collision where the impurity atom is so massive, so electron is going to simply bounce back just like a billiard ball. So you can think that most of its energy is conserved. There is no literally very much energy exchange between the atom and the electron. But then there is another mean free path, which is the inelastic mean free path. That involves energy exchange with the colliding entity. For example, collision with the phonons. Phonons carry momentum. Phonons carry virtual momentum, just to be precise, and they can exchange energy with the electron. Then it is going to lose its initial momentum and also energy. Another example is electron-electron scattering. That is also an example of inelastic collision, and the distance between two inelastic collisions is the inelastic mean free path, usually referred to as L inelastic. Okay. Another important parameter is the phase relaxation length, L phi. Electrons are quantum mechanical entities, and they have a phase term. The phase is also very important, and the distance before the electron loses its phase information completely is called the phase relaxation length. Generally, the elastic scattering events does not randomize the phase, it only shifts. Okay, but the inelastic scattering events generally randomize the phase. So you have to identify the inelastic scattering length as the phase randomizing length or phase relaxation length immediately. You can have many elastic scattering events occur before the phase information is completely lost. Suppose elastic scattering will preserve the phase. When I say preserve, it only will shift, but you can track it. Okay. So generally, the phase relaxation length is greater than the elastic scattering length. So you can have many elastic scattering events before the phase information is completely lost. Okay. There is another term which becomes important when you discuss the motion of electrons in a magnetic field, condensing magnetic field. Okay. So the extent of wave function in the presence of a magnetic field is called magnetic length. You can kind of say that magnetic length is very similar to the cyclotron orbital extension, spatial extension in presence of magnetic field. So the wave function gets a spatial extension or the spread when you apply magnetic field. Applying a magnetic field will cause electrons to undergo a simple harmonic motion. So it is similar to the application of magnetic field is kind of setting up a harmonic oscillator, a parabolic potential well, and the magnetic field or magnetic length is defined by this term h bar by EB over raised to the power 1 by 2. And there is another term called spin defacing length. That is the average length or spin information is lost. So if you define a spin of an electron to a certain direction, that information will get, or that parameter will get randomized, or the spin will flip after that length. So that is called spin defacing length. Okay. Then there is another very interesting concept that is called charging energy. That is not really a quantum mechanical phenomena, but it always be observed in three-dimensional quantum confined systems. So that is the energy that one need to exert to add an electron or remove an electron from a system. That is called charging energy. Classically, it's a classical quantity. Classically, it is defined as E square by 2c, where E square is the charge of electron, E is the charge of electron, and C is the capacitance of the system. So assume that you have a very small, say, quantum dot, and you want to add one electron to it. So the energy that you need to exert to add an electron to it is defined by charging energy, E square by 2c. This is a very small quantity when you consider the actual magnitude of E square and c. But when you have systems in the nanometer or submicrometer range in regime, then the c can be very, very small. And in that case, this quantity can be appreciable or substantial compared to the other energy scales in the system, such as temperature, especially at low temperature regime, like below 4 Kelvin. So this charging energy is generally observed in cryogenic environment. But if you have nanoparticle where you can actually connect using electrodes to run some current through it, then you will see the effect of charging phenomena. This is called single electron charging phenomena. That also we will discuss in detail in one of the coming lectures. All right. Now we have discussed most of the important parameters which defines the transport mechanism. And the transport mechanism is classified as diffusive and ballistic. Then there is classical diffusive and classical ballistic. Then there is quantum diffusive and quantum ballistic. So there are actually 4 transport regimes, out of which what we will concentrate is quantum diffusive and quantum ballistic. And classical diffusive is the transport that you discuss when you talk about Ohm's law. Okay, where you consider the dimension of the system, which is L here, is the largest compared to any other parameters involved. Okay, and you also consider that this L phi, that is the phase preserving length or the phase relaxation length, is really negligible because it's a classical system. You don't need to even worry about phase because we are not talking about wave nature here. Okay, and then there's classical ballistic regime where again the length of the system or size of the system is most important, and that is much larger compared to the Fermi wavelength. Of course, that is true because Fermi wavelength, the concept itself comes from the quantum mechanical treatment and it's a classical transport, so you don't need to worry about that. But when I say ballistic, what that means is the scattering lengths, especially the elastic scattering length, is much larger compared to the size of the system. So here, ballistic means the system, the electron goes through the system like a bullet. Okay, there are no scattering. There might be one or two elastic scattering, nothing. But diffusive means that is, as we discussed, it is the classical transport is driven by collision phenomena and the Maxwell-Boltzmann statistics. That is the Drude's theory, okay, of transport. Then when we come to quantum regime, there are two regimes. One is the quantum diffusive, and quantum ballistic. Whenever we say diffusive, the term that is going to project out all the time is the size of the system, which is greater than the collision or the, and also the de Broglie wavelength or lambda f, the Fermi wavelength. Okay. Now, quantum means this phase coherence length is larger than the elastic collision length. Okay. Now, ballistic means it doesn't undergo many collisions when it passes through the system. What that means is the length of the system or the size of the system or dimension of the system is less than the collision length, and also the phase preserving length or phase relaxation length. That means the phase of the electron is also preserved as it goes through the system. Okay. Now we have four regimes of transport, and there's one more thing that we need to discuss. As I told in the previous slide, it's not really a quantum phenomena, but that you can observe because of the quantization of charge, because electronic charge is discrete, or electrons are discrete. Electrons carry quantum of charge. Okay. Again, if you take a large macroscopic object such as a resistor, that has a capacitance, say, assuming nanofarads. Okay, whereas this E square term is really small, that is 10 to the power minus 19, and when you take the square of that, that will be 10 to the power minus 38, then nanofarad capacitor, which is in the denominator, you're talking about E square by C, right? There's a two factor also, which you can consider, but it's not going to make much of a change here. This is really small, okay, almost close to zero. What that means is, at any appreciable temperature, any low temperature, you cannot observe this phenomena except at absolute zero, because the charging of one electron doesn't take much energy. It's really small. You can calculate this number, 10 to the power minus 38 divided by 10 to the power minus 9, that is like 10 to the power close to 10 to the power minus 30. It's really small. It is far less than the temperature. But when you have small objects such as nanoparticles or quantum dots, then this term C will become very small. That can be in ordo-farads to, or even smaller. Then this number at low temperature range can be greater than kBT. That is the temperature energy. Then the charging and discharging of the system or of the nanoparticle is basically forbidden because the temperature doesn't have enough energy, and we need to supply sufficient energy to overcome this charging energy. That is actually called Coulomb blockade, which we will discuss when we discuss quantum dots in detail. Okay, and this chart kind of summarizes what are the size scales that one need to reach to observe this single electron or this charging phenomena. That is 4.2 Kelvin or liquid helium temperature, you can see for less than 5 micrometer. If the size is less than 5 micrometer, then you would see this phenomenon. If it is liquid nitrogen temperature, then you need to be in a regime where the size is less than 100 nanometer. But if the size is less than 10 nanometer, a few nanometer, then you can see this phenomena even at room temperature. This charging discharging event. Remember, as I told, this is not a quantum mechanical effect. So we are not talking about, let me emphasize that point, we are not talking about single particle energy levels here. Single particle energy levels come from the quantum mechanical treatment. That is not what we are talking about. We are talking about the Coulomb repulsion driven charging and discharging events in the classical transport context. All right, so that is the summary of various transport regimes, and in the next lecture we will start looking into the low dimensional system. We'll start with metal semiconductor interfaces, then semiconductor structure, then we will march down to two-dimensional systems. All right.